let us look at how the solar irradiation can be calculated. This is based on a paper published very recently in 2016. So here this model is basically based on the temperature difference and the relative humidity. This is used to measure the solar irradiations. This model was checked and on 8 sites in the Norway for 10 years. So that means it's quite a bit long time people had actually carried out this analysis, and the performance of the model was actually evaluated through statistical measures, and the results obtained are acceptable. In other words, it is a robust model people had developed, and they have been measuring it at 8 sites for 10 years. That means they have enough data to understand how it is actually performing, and the equations are given here. So here the RS is the estimated horizontal global solar radiation, and the equation is RS equal to 0.04 into RE. RE is the extraterrestrial solar radiation into T max minus T minus. That means what is the maximum and the minimum temperature for that particular day, plus Ct is a constant which varies geographically. So this is the one parameters when we talked about the empirical parameter which may keep changing. So this Ct is the constant which is used to address that particular deficiency. And again Re into Rh to the power 0.27. Here Rh is basically the daily average ground measured relative humidity. So humidity also plays a vital role in the amount of sunlight received by the earth. So they used humidity and the surface temperature to figure it out what is or how much of the solar radiation received by the earth. And here is another equation where they have used the sign values. That means what is the how much degree it is deviated. So all those and the bathymetric informations are also included in this particular equation, so that they exactly know how much, because this is at 8 different sites. So all of the sites will have different geographical placement. So they measured it and they figured it out. This model works completely well. Let us look at what are the physical, chemical and biological processes that are affected by the solar radiation, because we have seen that a plant is affected because of the photosynthesis which is going to get affected. So similarly, what are the physical, chemical and biological processes that are affected due to solar radiance? So the one is the black body radiation, the other one is the albedo effect. We will be looking at albedo effect soon. Greenhouse gases, aerosol and dust. So how these affect the solar radiation received by the earth, that also we will see. And in the chemical process we have photosynthesis, photovoltaic effect and molecular solar thermal storage, photochemical reactions, free radical generation, photoisomerization. So these are all the various reactions which can be carried out by photo, that means sunlight. And some of the biological processes that can be possible include biosolar cells and photosynthesis. So these are all the various processes which are affected or which can also be carried out by solar radiation. And let us look at the photomineralization process. So photomineralization means using photons or the solar energy, we are mineralizing something. So that is the major process. So that is why it is called photomineralization. So here it is basically conversion, means mineralization means it is getting converted to solid or similar to that. So here the photochemical degradation of the dissolved organic matter to carbon dioxide is called photomineralization. So carboxylic acid is treated with oxygen and it gives RH and CO2. So here the photochemical degradation of the dissolved organic matter by sunlight happens. So here we have the permafrost. We will be looking at what is permafrost. Permafrost means permanently frost. In Arctic, most of the soil is actually in the form of permafrost. So there we have dissolved organic matter in the soil, and we are now looking at how the dissolved solid organic matter is getting converted and how CO2 is liberated from this dissolved organic matter. So that's what we call like a photomineralization reaction. So sunlight falls on the DOM, that is dissolved organic matter, and it leads to photo degradation. This is one set of reaction that is happening. In the other set, what happens is there is also aromatic carbon containing dissolved organic matters. So they undergo various type of other reactions. One is some of them is getting converted to phenolic carbons, and the antioxidants which are present convert them, leading to ROS quenching, that is reactive oxygen species quenching happens. So this is one set of reaction. And of course the aromatic carbon may be getting converted to aliphatic parts, and the aromatic carbon may also decompose to give hydrogen peroxide, hydroxy radical, and singlet oxygen. So these are all the three different reactive species that may be produced, and these reacts with, when we talk about aliphatic carbon, it is basically conversion to fulvic acid. So that is the structure of the compound is given here. So when any organic matter has carboxylic acid, the reactive oxygen species, mainly the singlet oxygen, reacts with it to liberate carbon dioxide, and here what happens is there is an exchange of oxygen takes place. One of the oxygen from the carboxylic acid is replaced by the reactive singlet oxygen. So that is how here you see the red color to blue color change. So the red color is now captured on the carbon dioxide which escapes, and this reaction is called as the photomineralization reaction. And this terephthalate is known for the probe for hydroxy radicals that produces a fluorescent product, hydroxy terephthalate HTPA on hydroxylation. So this reaction is actually used to measure how much of the photon energy is received. So to measure that, this reaction can be used. So the terephthalic acid is converted to hydroxy terephthalic acid. So here the reaction occurs in the ortho position. So this reaction can be used to monitor the photochemical hydroxy radical produced, because in the previous slide we have seen that the hydroxy radical is produced in this particular decomposition reaction. So that hydroxy radical is measured, and here this hydroxy radical is produced by the nitrate and dissolved organic matter. All of them produce this hydroxy radical. All this reaction happens in the presence of sunlight. So how much sunlight falls, depending on that how much hydroxy radical will be produced. So based on measuring the hydroxy radical, we can indirectly find out how much solar radiation was received by that particular matter, soil. So that is how the back calculation we can carry out. So the TPA is very selective for hydroxy radical with respect to singlet oxygen. So this is even much more accurate of figuring it out, because solar radiation produces both singlet oxygen as well as the hydroxy radical. So this particular TPA probe is mainly used for measuring the hydroxy radical produced alone, so that we know exactly how the photochemical reactions are actually happening. And TPA did not undergo direct photolysis. In other words, this is a direct method of measuring how much sunlight received by the materials. So here is some of the instruments that are used for solar irradiation measurement. One is the pyranometer. So here is a picture of the pyranometer. These instruments measure global solar irradiations, including the direct sunlight and diffuse sky radiation. And we also have pyrheliometers. So these measure direct beam solar irradiance, and they are also used in conjunction with the solar tracker to ensure accurate alignment with the sun. So this is another instrument to see where the sun is actually located, because in the previous equation we have various angles we had. So one of that angle is, where is the sun? Actually, is it exactly above our head 90 degree, or it is at a tilted angle, or at whatever is the angle, starting from morning 9 o'clock to evening 5 o'clock. So how much is the angle? Because the material of under study is here, and we are going to see what is the angle that is formed here. So that is measured using pyrheliometers. And we also have satellite sensors. So these also provide a large scale measurement of solar radiation. So these are all some of the instrument that is used for measuring solar radiance. So let us look at what happens to sunlight when it hits Earth. When the sunlight hits Earth, three major events happen. One is absorption, another one is reflection, we call this as a albedo, and the transmission, that is 100% of sunlight is being reflected, is happening. So one is absorption, another one is reflection, and the third one is transmission. So these are all the three events that are happening when the sunlight hits the Earth. So absorbed radiation is basically converted into thermal energy, that is by the land or water, or electricity if you use solar panels or photovoltaic cells, or maybe for chemical bond formation in the case of photosynthesis. So the sunlight can be used to carry out different types of reactions. So the absorbed radiation is responsible for it. And then reflection is a process of redirection of the light when it hits any surface. So the major type of these reflections are, one is a specular reflection. This is basically a mirror-like reflection, or diffuse reflection, which is like a scattered reflection. So these are all the two major types of reflections that can happen. In either case, there is a change of direction of the light. And the last one is the global solar radiation, consists of direct beam solar radiation and diffused solar radiations. Because how the diffuse solar radiation happens, this is due to the air molecules present in the atmosphere, or water vapors, clouds, dust, pollutants, forest fire, etc. So these are responsible for the diffused solar radiation. And let us look at the comparison between reflection and albedo. Reflection is a process of light bouncing off a surface, whereas albedo is the measure of how much of the incoming radiation is reflected by the surface. So one is process by which how the light is reflected, another one is the measure of how much is reflected. So one is called reflection, another one is called albedo. So the albedo is basically a dimensionless quantity and ranging from 0 to 1. That means either 0 means total absorption, 1 means no absorption. That means 100% reflection. Albedo is the ratio of the reflected radiation to the total incoming solar radiation which falls on that particular surface. So reflected radiation versus radiated energy, when we talk about, the energy here is related to the bulk of the material, whereas the radiation relates to the medium, that is rarer to denser medium transfer. Let us look at one important effect which is called the projection effect. The projection, insolation means incoming solar radiation from the sun, which is received on the earth in short waves. So this is what is called insolation. So incoming solar radiation. The angle between the surface and the sun moves from normal 90 degree. The insolation is reduced in proportion to the angle's cosine. So that means when, let us look at, this is our material which receives the solar radiation when it is exactly above its head. So that means when the angle is 90 degree, so it receives the maximum sunlight. This area receives the maximum sunlight. So here when we want to calculate the insolation, so the angle is 90 degree. So here the insolation is 1x at 90 degree angle, because this is the angle between the ground and the sunbeam from where it is coming. And when we look at the sun at maybe in the early morning or maybe in the late evening, we can see the angle is around 30 degree. So when the angle is 30 degree, then what actually happens is here this angle is 30 degree means the horizontal plane is at 30 degree, but the actual angle is 60 degree. So cos 60, when we calculate, that is 0.5. So instead of 1x, the sunlight now covers an area of 2x. So what do you mean by this? Why we have to understand this projection effect? So the projection effect actually plays a vital role. In other words, we had seen the equator receives 100% of the solar light, whereas the poles receive only 40% of the solar light. So what is that reason? The reason is nothing but this projection effect. So in the equator, the sun is exactly above its head, that is 100% it is receiving. But at the pole, it is above 66 degree north. So that means the angle is highly small. In other words, when the sun is far off and it actually covers larger area, the amount of solar energy hitting that area increases. In other words, if you look at each individual spot, then they will be actually receiving much less energy. So that is the reason the projection effect helps us to understand why the polar region receives less amount of energy. So the amount of absorption and the scattering of sunshine basically depends also on the nature and the concentration of the air molecules and the small particles in the atmosphere. Of course, if it is more cloud, then the amount of sunlight received by Earth is going to be less. The solar radiation actually has lower intensity in the polar region because the same amount of solar energy now heats more area. That's what we said. Due to the projection effect, we can see the amount of solar energy received remains the same, but it now has to heat up more area. In other words, every area in that particular region is going to get less sun energy. So it becomes less efficient. So this projection effect is the main reason why Earth polar regions are much colder, because they receive less solar energy than the equatorial regions.